Our presentation is a continuation what Dr. Pat Diamond and Sam Metheny did. We'll show you how we build the system and how it works. To explain that, we have to go just a little bit to show you the physical layer, bits and pieces, so that you understand the motivation, why we designed the system and how we designed it. I'll first start with ATSC frame structure. This picture is from the standard. You see that the first, the orange block, that is one frame, and it starts with bootstrap signal. That signal was actually designed to signal that everything follows the bootstrap is ATSC3. It was broadcasters envisioned that in the future, they might want to send a totally different kind of waveform. So they just need to change the bootstrap and send a different kind of waveform. So ATSC3 receiver or receivers of just one kind would listen to the bootstrap and know whether to ignore the rest of the frame or not. So that's why it was designed. That signal was designed to be detectable at minus 12 dB SNR. And Sam already mentioned it, the sum of the broadcast hours transmit 1 million watts. It's huge. And even if you transmit 1 million watts, and you can, on the receiver side, you could receive at minus 12 dB SINR. So that signal is really robust. So then right after bootstrap, the other signal is preamble. Preamble tells about what is, how the payload is configured. If you come from the 5G world, this is the resource block. This is also FDM, the time frequency resource block. Those we call PLP in ATSC3, physical layer pipes. Similar concept, same thing. And actually the same people designed both. Preamble is also robust signal. It's detectable at up to minus 9 dB SNR. In the preamble, within the standard, there are fields. You see the name of the fields to put a timestamp in, and the reference point, like what the timestamp refers to, is actually the beginning of the bootstrap. So in this configuration, we will have a reference time, and we know how to put a timestamp in. So this is already in the standard. What we have added, which is also the standard supports, and Sam Metheny was talking about it, is just ATSC standard transmits data. So we added a data portion, and that data portion carries the location of the tower. So remember, Sam has a picture, but it was say not to the scale, bootstrap preamble, and that is how it's done on the payload piece. One thing that ATSC3 allows is you can control the quality of service of the bits. It's a payload, and you could choose modulation, the constellation, all the way to 1024 QAM, and on the other end, QPSK. You could choose different rates of error correction. The lowest is 2/15th. So if you choose QPSK constellation and 2/15th error correction, you get a really robust channel, especially if it's coming out from a 1 million watt tower, just a mile away, a few miles away. So the way to, at the receiver or to synchronize the tower, any way to get the time, you can have many clever algorithms, but one of the simplest way you could see that you detect the bootstrap, extract the bits, recreate the signal that was actually transmitted from the tower, correlate for different frequency offset. You could use ambiguity function. Like if you're in that, if you know that there are known signal processing techniques and implementation techniques to do that. So you correlate, you find, okay, I see the bootstrap signal starting at this point. And if you're time stamping the RF samples, that now you have a time. And then you decode the message to find what time is when the first sample of the first symbol of the bootstrap started going up, the rising edge. That's what the time is. And then you have to decode the payload, which has the location. It will actually have other things that Mark Corl will show you and explain, because towers can listen to each other, so we have a whole message structure. But for the basic operation, that's how it works. Now, this is the transmit chain. So when you have a frame structure, it's really nice. Here, bootstrap comes first, then preamble that has a timestamp. But when they're created in the transmit chain, it is not in that sequence. Timestamp is created somewhere in the middle of the chain, and the real waveform is created sometimes later, the second block you see. And then the signal goes, this is still in the digital domain, and then you have to convert digital to analog, and then it goes to the analog equipment, amplifiers and transmission line. And transmission line is huge. It transmits 1 million watt. It's this thick, copper pipe, runs 2,000 feet. So all these things have delays, and with temperature change, with wind, and it's moving all together. One way, initially we thought that we'd characterize the delay, the hardware and software delay in the digital domain, and on the analog domain, if you could measure it with, there are devices to do that. It's a little expensive, but you could do that. Then maybe one shot we could do the time. Then with all the variation, then with the new, maybe with the new software upgrade, someone changes something in the transmission chain, because the orange boxes you see, they are not like one device. They're different piece of hardware. So you could mix and match, swap, then we have to recalibrate the whole thing. So we think that it should be actually done in a loop. So we constantly synchronize when the timestamp. This picture shows in the gray on the bottom is the existing transmission chain. So this is already happening in the television stations and everywhere. There are many other blocks. It probably will take 20 more slides on the, if you go upstairs, you can see how complex the television station is, all the way that comes to the video. We're just showing at the very end of the digital domain what happens. So we have a detector, a sensor, that detects, actually looks at the transmission that comes out of the transmitting antenna, decodes the message, and it also doing by correlation, it finds the time of arrival, looks at the time, and then using a reference time. As Sam Anthony mentioned that we are using GPS here, but it doesn't have to be GPS. It needs to be an authoritative clock that is traceable to UTC. That's what it requires. And so with the reference time, we decode the message and then see if the timestamp is right or not. It says whatever it says. And if there's an error, we take the error, feed it back into the loop to make the corrections. And people who have worked on control theory, you don't always just take, then the loop becomes unstable. There are techniques, and these are, people have been working on it for 70, 80 years. And so there are techniques that you can have a loop filter or some sort of controller in there that averages the error and feeds it back into the system. And that is actually the loop. You're listening to the real transmission. Using a reference time, we measure the error, and we feed back the error. We ask the system to adjust. If it's 20 nanosecond early, you have to return a little bit, a couple of loops, and it'll adjust to 20 nanosecond. So that is actually the loop and the synchronization loop. And on the first prototype we did that. We have done another prototype. We have a better performance that Mark Corl will show you later. But the purpose of this demonstration and the prototype building was to show that this synchronization actually works with existing equipment. We don't need to do anything. Existing standard is totally compliant with the standard. And today we'll show you a demo, and Marco will show you screens, and I just explained what the demo is. You see on the left side is the same picture I was explaining. There's a tower, and the signal is coming out of the tower. We have the synchronizer. The synchronizer is our sensor. It extracts the timestamps. It measures time of arrival. You see if it's the right spot or not. Then it feeds back to this equipment that actually changes the timestamping process. So that timestamp is very accurate. And this happens on the transmission side, which is actually 1.5 kilometers away. It is happening, is being synchronized using a GPS clock, but that is not the point. We could replace it with an expensive clock if we want to. So it's happening totally separate, 1.5 kilometers away. And then in this building, we have a receiver. And that receiver takes only BPS signal, nothing else. It just takes BPS signal, it measures, extracts the time, it has its own oscillator, it aligns it, and then it also produces 1 pulse per second signal, which is standard in the timing, like everybody measures how accurate this 1 PPS is. So this thing produces 1 PPS. Then to compare it with GPS, we have a GPS receiver, and we also take 1 PPS signal and put it on a scope. And then we see, we are triggering, if you're on an oscilloscope, we're triggering a GPS signal and letting the other signal run. And we see that this 2 signal, the BPS pulse, is within less than 25 nanosecond of the GPS 1 PPS. 25 nanosecond. And we don't even have a line of sight. And the transmit tower, as I heard, is only 20 feet tall. And it must be low power. It still works. And there was a question before, during Sam's presentation about clocks, what to use. There's a whole community in the PNT industry that sells clock, that makes clock. So that community or those manufacturers have come up with solutions. They call it a clock ensemble. So it's not just one clock. It maintains it maintains its time, but it takes many input. And Andrew Hansen was talking about, like, you could have complementary inputs to it. One of the accurate input is you could get it from PTP or fiber. Some of the fibers, they get fancy. If you calibrate it, it could get like a few nanosecond accuracy, time transfer from NIST. That is the time. If they say this is UTC, this is UTC. So you could get time without GPS through fiber. You could get time through atomic clocks. Those are also well understood, well known. They're rather expensive. You could just a cesium clock could be a Mercedes S-Class. So you could think about it. So you don't want to use too many of those. But so that's already existing, and this ensemble. It can also take GPS, no harm in it. As long as GPS is not the only source, we're fine. GPS is the most accurate. So if you add GPS to this group, this will perform actually better. I think GPS is very accurate. But remember, Sam was saying that's 17 towers on the average, and if you mount the antenna 50 meters high, you could get 70 signals. What are you going to do with the signals? We could use it from one tower that has a very good clock. If it's a leader tower, you could transfer the time to other towers. If you have 70 reliable clocks, And if you listen to the 70 clocks, average them over, I don't know, you're saying a 10 to the power minus 5 with 17, with 70, I don't know, minus 9 maybe? So you could have, you can have a clock that reliable because you're listening to each other, all the towers. But this kind of product, this is not like required, this is not part of the ATSC standard or part of the BPS, but these things will be used when BPS is deployed. Maybe 10% of the towers will have this sort of clock. This is an authoritative clock, they're traceable to UTC, very reliable. And then other towers will listen to them and synchronize their own clock with these. In terms of future improvement, so far we have talked about what we have done, but there's also, I think there's room to improve the system. The first one is, as we are timestamping, we get the timestamping error, we are synchronizing the loop. That's totally fine. But the receiver that has received the signal, say the timestamping error was 5 nanoseconds. The receiver will have that 5 nanosecond error in there. But if we send that on the previous frame, there could be about 5 frames per second. On the previous frame, when he tried to align, it was just 5 nanosecond or 15 nanosecond off. You can use that information in your estimator, whatever estimator you're using, and adjust for it. Then the 15 nanosecond error that we already transmitted, next time you can say, okay, by the time whatever I transmitted, 15 nanoseconds subtracted, that is your time. And that was the time when you send the previous frame. So if you're running your estimator as a clock, you could adjust and you could get more accurate estimation. That is one. And it's easy to do. It's just a message structure, and we already have the errors. The second one is, all these towers are listening to each other. So why not, we put a sensor on every tower, listen to what's the timing that is transmitted to all the towers, and pack it up in a message. And ATSC3 has, the data pipe is really big. So you could actually broadcast these messages for all the other timing for the other tower. This will actually help other towers, not only that one tower, like I'm transmitting, I'm also getting feedback, I could be off. So there is a way to synchronize each tower. That is one opportunity. Another opportunity is, if you have a receiver, remember our receivers are passive receivers. It doesn't have any uplink or anything. So these receivers will receive the report a timing information from one tower, and also the quality of the time from many, many other towers. So receiver can decide whether it should take that timing information into his consideration or not. If the tower is out of sync for some reason, or if someone spoofs it, it could readily detect. Like, you're saying that you're transmitting at time t, but everybody is saying you're transmitting at time t plus delta. I'm not use your time. I'll use 16 towers, not the 17 one you get rid of. So that is the second application. It's easy to do, but it will make the system really resilient. And the third one is, if all the towers are listening to each other and sending time to each other, there's an opportunity to make all the network of all the tower a mesh of self-synchronizing network. You can think about it. It's like all the towers are listening to each other. They're all trying to track each other, be within a range of each other. And if you seed the market with 150 authoritative clocks or something, the whole nation will have reference clock. It's mesh network. And this is something Mark Corl will show in his slides, and he will also show you the data structure. how it's done, and we have implemented. We're going a little bit deeper, but we just want to give you a flavor of how we have implemented it. And then at the end of our talk, we'll show you a demonstration. Those, remember, signal coming 1.5 miles away, producing 1 PPS pulse. This one, GPS produces 1 PPS pulse, and they are within 25 nanoseconds, they're aligned. All right, Mark?
Okay, let's go to the next slide. So I don't have very many slides, and I usually like to stand in front of them, but that's fine, I'll do it over here. So as Tariq said, really what we're thinking about going, well, first off, I'm not a time guy, so don't ask me a whole lot of stuff about time. I don't know. He knows. He knows. I don't know. You know. But I don't really know. I'm a systems guy. I mean, I like doing systems stuff. I like putting systems together. I like figuring out how they're going to work together. That's what I do. And standards, as you might have heard from the introduction. So what really I was trying to do up here with this slide is just give you a notion of that there's a few leaders out there that would have the really accurate clock and traceable time, and that there'll be some followers that can actually see the leaders and then adjust their time as appropriate for the leaders. So this was just sort of setting context for what we're considering in sort of our next deployment, or at least our field trial deployment. So the idea here, this is the synchronizer that Tariq talked about. This is something that Avateq developed, and it's running. This one is running, and we'll show you the screens for this, and that it's actually physically running in the transmitter site that's 1.5 kilometers away. That's running with a loop that's connected back into the regular system, into the broad. I just simplified this down to just a broadcast studio, so there's some time fine tuning, easy for me to say, going into the broadcast studio, and then this is the loop that Tariq was just talking about. Now in the real deployment, what we would do is have other receivers. What we're calling them today is a validator. So there's a validator upstairs that's looking at this same broadcast that the synchronizer's synchronizing. And there's one of these upstairs, and it's feeding information back into the system, and we'll take a look at that. And that's the thing that's being compared. So I do want to make the point, this is the first time here in Canada, at Humber, is the first time that BPS has been actually on air. Anywhere in the world, you're like, this is it. This is the first time. Vlad deconstructed his lab to put it over here and actually have it on air. So, I mean, you're in the, this is unique. This is the first time this has actually been on air. And we're doing it here in Canada, at Humber, which is good. I consider Humber my sort of experimentation lab. Oris doesn't really know that, but he does now. So we're doing a ton of really cool stuff here, and you can, later on, you can actually go around and look at what's happening up in the lab upstairs. Really cool stuff happening here, and really interesting out there stuff that Oris and the lab are doing, and this is one of them. So what I was really trying to show here is just the fact that we can see N other transmitter. Now, Tariq, there was talk about 17. There's talk about 70. Depends on how high these antennas are, really. And if you got a tower to work with, you can put antennas up and down that thing, so you can do whatever you want, as high as you want, depending on how much wire you want to deploy, and then how many of these you want to buy, these receivers. And as we go forward, as we deploy, if this gets deployed, we expect those receivers to become relatively inexpensive. And what they're doing is taking the neighboring information and forwarding it off to what we call the BPS info. So BPS info is that data structure that Tariq and Sam and everybody referred to, which is the data structure that describes where this transmitter is physically, how high the antenna is, where it is, X and Y. And that information is over here, the position information, and the measurement information that these things are pulling in, like how close is the time to the time that I know about. So This line, this double line that goes up the back is the traceable time reference. And so all these receivers have to know where traceable time is, whether it came from GPS, whether it came from wherever. As long as it's traceable, then they can measure where they are, where that signal incoming is relative to that, and then tell you how far off it is, plus or minus. And that all gets fed forward and added into the data structures. The other thing that's happening, and this is the clock reconciliation that Tariq was talking about, we could have multiple clock references going into this, and it will pick and choose which one it thinks is the best. And that technology exists, and it's just a matter of deploying it. So most of this is actually pretty much done. This stuff has to be done, but this is just as a software guy, I could say that, just manipulation of data, moving data around, storing data. So a little bit of look at what's actually in the BPS structures, and they're color coded, but that's fine. So the information data structure, and we're still trying, or at least I'm still trying to figure out where we want to put these data structures and how often we want to send them. There's thoughts about putting them at very low levels in the data link layer of ATSC or at the IP layer. Some we might put at the IP, some we might put at the data link. We're not quite sure yet because it depends on the timing. So the measurement information over here tells us the bootstrap times, the accuracy and the offset of the neighbors, plus the previous time and error from the current in the synchronizer case. This happens every frame. This happens every time a frame is measured. And those are sent fairly frequently, as many as 5 times a second. It can actually be faster than that, but generally we're running them about 5 times a second. So that information comes pretty quickly, but fortunately it's relatively small. In fact, all of these are pretty small. I think I figured out each of these fragments is roughly, I think about 60 or 70 bytes. They're not a lot. It's really not a lot of information. But what we've done is we have a single data structure, and we can mix and match these any way we want to in the data structure. But each one of these fragments contains a unique transmitter ID. Now that's a harder problem than it sounds. They aren't really ID'd. If you're in an SFN, they have an ID, but finding the actual ID of a transmitter anywhere in the United States or Canada is not, and uniquely identifying it is not exactly easy, it turns out. There's 3 fields that we're actually using right now in the software. One of them being transmitter ID, but then there's some other stuff, because the transmitter ID just tells you what part of the SFN it is. But the fragments can be grouped any way we want, so we can actually move them around. So we did that as part of our second phase and manipulated that, and it makes it a little bit easier to manage. And you'll actually see that on the demonstration. But essentially what this data really does is provides an equivalent of the GPS almanac functionality. It's kind of the information that you need to know about where these things are and how well they're performing. So the timing source fragment is basically, what is this transmitter using for timing? I might not want to use, for one, it might be an offset from a leader. It might be third down the line or something, in which case it's used, maybe some less than perfect. If it's 0 here, then it is the leader, and I know it's probably using a time source that's very tightly bound, if you want to say it that way. Now, all of these are going to be tightly bound ultimately, but this one will know that it's using a cesium clock, for example, or it's going to be using PTP, or whatever it's going to be using. So that information tells me what time source the transmitter is actually using. And then lastly is just, where is the transmitter? And some aspects. This is the position, but there's also information about where it's pointed, what's the gain, how much power is it generating. So I'll know a little bit about where that transmitter is and how the data is getting to, how much energy is being pushed at me. And then it's also information about the antenna field pattern. And that shows back. So, Vlad, that was the last slide in this group. So now we're going to show you the demo, the actual moving. I'm going to have my lovely assistant drive the Yeah.
How many people here? I'm just curious. We're using the word traceable. as though it's something that people talk about. I don't think so. How many people here know what traceable time really is? Not very many. How many of you would like to know what traceable time really is? Okay. I'm going to tell you what traceable time is. In the time distribution world where you're dealing with standards, whether it's IEEE, whether it's IEC, whether it's ATSC, whatever it is, if there is a time boundary in there, it's got to be traceable to something. And traceable means that you have a methodology of tracking the source of that timing back to what's called universally coordinated time, which comes from the International Weights and Measures of BIPM in France. So in most of the very high-end timing systems, one of the functions is traceability. So if you're a bank or you're a power company or you're a telecom company and your regulator comes to inspect how you're doing, one of the things they're going to have you do is prove to them that your time is traceable. So you have a system that shows them in data they understand what traceable level are you? Are you traceable 1, 2, 3, 4? How many nanoseconds to precision time is the traceability? And does that satisfy the standard performance that you guarantee that you satisfy? So that's what traceability means. And I'm sorry I didn't mention that earlier today, but sitting here listening to Mark, I was thinking, I wonder how many people have ever used that word. Anyway, that's what it is. If you have any questions about it, I'll be happy to talk to you about it later.
Thanks, Pat. And while Pat was distracting you, go back to the O-scope. I want to show that in case it breaks. We've been having trouble. This is an O-scope. How many people in here have used an oscilloscope that actually connects to the web? And you can watch the video on the web? That's what we're trying to do here, right? So worse than that, it's on a machine up there, and this is VNC'd into that machine. So little bit of smoke and mirrors here, but the point of all this is that is actually, this is the one BPS signal. I don't remember which one is magenta.
Yellow one from regular GPS receiver.
Okay, so the yellow is from regular GPS, and the magenta or whatever that color is from the validator. And you can see when the spike happens here, you can't really see it. They're 25 nanoseconds apart. So that's basically BPS operating, and it's pretty fixed. It's not jittering very much at all in this space here. And it pops up there every once in a while. So I declare that a huge success. And it's operating, the goal was close to that, but really if you remember all the other slides previous, 200 nanoseconds was kind of the bar, and we're well below that. Let's go to the synchronizer, other display. So that was upstairs, and you can go look at this later. That oscilloscope and the validator is upstairs on the 5th floor. Yeah, so this is the synchronizer. This is out 1.5 kilometers away at the transmitter site. This is basically the jitter. This is the measurement happening when, as Tariq described, you have the first symbol coming off of the transmitter, and you're measuring that, and this is the measurement of that transmitter, the time of arrival of that transmitter, of that signal, of that bootstrap, compared with a reference time. This number is 0.008, which basically is 6, now 5, now 4 nanoseconds. So this is the swing around 0. And you'll see it shift every once in a while, but the key is that it's staying well under, usually under 10 nanoseconds. And I haven't seen it move much under, it's usually under 5. So when we were doing this before, this swung into the 300 nanosecond range. That was phase 1. This is phase 2. So in a course of basically 6 months, we've gone, almost 2 orders of magnitude. So and that's with dedicated now. We haven't had a lot of funds, Vlad will tell you. So we've been doing this on a shoestring. So, but I think it's impressive work by Vladimir and the Avateq team. Hats off to them. It's unbelievable. Let's look at the BPS. So we can look at both the emission side and so this is just the fragments that are being emitted. Now these are dummied up. Some of it is dummied up, but we are actually using the position information on the receive side to tell us where that transmitter is out there in 1.5 kilometers away.
And the signal is very not weak, huh? No, it's okay. The signal is 64 minus 64 is
Oh yeah, that's. Oh yeah.
minus 64.
Yeah, so it's minus 65 dBm, so it's pretty low.
That make it very low.
But it's all being picked up. So this information is being broadcast. This is the BPS information that I described. This is the validator, right? Yeah, this is the validator that we're looking at, and it's just pushing this information. Now our next phase is to really think this through and build a network, at least a lab-based network, and move this information around as appropriate. Like move the measurement information around frame by frame and make that frame moving around in frames. The other thing we've done that isn't here, we've synchronized with exciters. So that feedback loop that I showed, that isn't quite done yet. We're still in the process of doing that. We've got it synchronized with what's called the gateway. And so we can manage it that way, but that loop is fairly broad. It's not as tight. If we go with the exciter, we probably will do both, honestly. If we go with the exciter, we can manage it right at the edge of the emission. So right now, that's what we're working on. We've got the protocol defined. We just haven't, we're right in the middle of troubleshooting it, honestly. Let's look at the validator. Let's look at the BPS and the validator. The validator BPS? Because this is the synchronizer, right?
This is validated.
Oh, it's a validator. Okay, never mind.
So they extracted.
Yeah. So this was extracted. This is the transmitter ID that was extracted, and this is the position that was extracted out of that. That's where that other transmitter is, physically. The thing that's doing the measurement is here. The thing that it's measuring is there. It's in the data structure, yes. I'm not answering the question you're asking because some of these were just dummied up. But we would, yes. My vision is that we'll have a nationwide database of all the transmitters, and then we'll be able to pull that data and use it locally, or if in an emergency situation, we'll have a local cache of it and send that out. So the position information doesn't need to go that frequently. Not frame level frequency. So this is the kind of sort of systems level thinking you have to go through and really decide how often do we want to send that. We may want it, depending on the other bandwidth that we're using, we may want to send that fast, we may want to send it slow. It depends on the use case as well. If we get to the point where somebody's doing a handheld, yeah, you want to do that pretty frequently so they can sync faster, right? But if we're doing infrastructure that's stationary, you don't have to do that hardly at all, if you have to do it at all. So we have to think through that whole process, and that hasn't done.
I'd just like to add that in the data structure, we have plans to add the power of the transmitter and also the antenna pattern. So this it will lead you to some AOA angle of arrival opportunity in the future, and also detecting spoofing and other stuff. We don't have to solve it, but we have plans to put it in the data, and someone clever will figure out a use of it.
When I'm thinking about practicality, I think it would be a point that you may change the settings depending upon how much the system is implemented. If you're starting out with a small number of stations, it's one thing, but when you get into larger number of stations, you can then change it. The beauty of this that just is becoming very clear to me is that it's very flexible. You can do a lot of different things.
And tell us how many stations you
We have, Sinclair, we operate about 200 stations, but it doesn't matter. I mean, it matters that the fact that there's a lot of stations out there. It's not going to be an all of a sudden stations are going to all change over. It's going to be a gradual kind of a transition.
I'm hoping for a sudden transition. Immediate, like next year kind of thing, but it's not going to happen. Anyway, questions. I think we've gone through.
Let me to add a couple of bills.
Okay.
From the very beginning. I don't want to talk. I just wanted to add a couple of notes. So the receiver, is it okay? The receiver, we integrated into the receiver from the very beginning a set of tools to detect, visualize, and measure spoofing. So any signal which interfere with the main BPS ATC 3.0 can be detected. It's a gray line inside. Even if it's hidden under the main lobe, we can detect it, we can measure it, and we can plot it. And what else? We provide a set of tools for very detailed analysis of the signal quality and transmitter system performance. And we think it's very important, especially at the early stages of the development. That's what I wanted to add.
Thanks, Vlad. The other thing that occurred to me that when we were talking about this BPS info, all the signaling in ATSC3 and all of the data that goes out can be signed. The signaling is required to be signed. Any kind of interactivity has to be signed. We could sign the BPS info too, so it couldn't possibly be spoofed. So that's a possibility as well. We just haven't. That's a sort of a different systems architecture, so I have to think that one through first, because we have to deal with PKI and things like that. So it's an interesting nut to crack, but we'll figure it out. Jim.
So knowing that we're talking about trying to receive many channels at the same time, what's the ideology for knowing what channels to look for? And is that a lookup table that travels with the device? Like, what are your thoughts about implementation channel-wide?
I think, well, Tariq might have another take on this, but I think it would be you would know the topology of your network, of your mesh, right? You would know. And to get probably a lot of the just resiliency, you'd probably want to pick and choose amongst the set. But again, that's going to depend on the deployment. That's going to depend on who's doing what. I wouldn't, if I was Sinclair, I wouldn't look at all my stations, right? I'd look at other stations on different frequencies, right? Because I wouldn't necessarily trust that the vendor that I had putting all this stuff in would always work. Maybe they break once in a while. Maybe there's a software bug, right? You want to basically take advantage of the fact that there are a large number of these things, right, in the area. And you might not have 70, you might not have 20, but by the time we get there, maybe there's silicon can do this and we can look at all 70. I don't know, we'll see. Right now, it's expensive to do 3, so.
Yeah, just like to add that we plan to receive many towers, but remember that we're expecting line of sight, but sometimes we may have multipath. So quality of time from all the towers will not be the same. It will vary depending on the distance and depending on the multipath. So we have the flexibility of mounting as many needed, possibly pointing to the leader towers, because there's a cost associated how many followers you want. But also we'll pay attention to the multipath and that clock ensemble. There are products that algorithms that figures out if one path has multipath is delayed based on the jitter so that algorithm already exists. So we'll have multiple input, but then we'll figure out the best time out of them.
Andrew.
Mark, Vlad, Tariq, this is exciting. So two questions. One will be what I was thinking about earlier, and then I'll come back to the spoof/multipath, and I'll expand on that. First, what kind of, I guess I would call it that ALPTP loop, what loop bandwidths are you talking about there? I heard you say 5 hertz. That seems awfully fast, but maybe not, I don't know. Okay. Because that's interesting in the far future, looking out. Okay, you're exactly. So the okay, fantastic. But considerations around that loop bandwidth are exciting also, because if someday we're driving for ones of, I mean, you're gonna have all kinds of physical characteristics about your transmitter. So that's exciting that you have that kind of loop back on your control. I want to jump to Vlad's point, and spoofers is. I love to immediately go back to the most simple spoofer in the world is multipath. Right, that it's a second signal that's exactly the same, it's just coming through a different route. The idea that you have designed in here is something that you are starting to at least be able to characterize, leaves you a lot of options later on that can be refined for the handset. So I applaud that effort, and maybe because some of prior colleagues, multipath was the gotcha, but we didn't have this standard and this level of baseline to work with. So keep going there. And the situation of multipath itself will lead you to other things that are interesting. There are lots of second order elements that multipath actually becomes good for. So keep that up. That's great to see that you've got it in your tool set. So thank you.
Yeah, so another nut we haven't cracked yet is SFN. So we're still talking about SFN. So speaking of multipath, it's very similar, but SFN is another one that we have to figure out. I think we've got some ideas that we want to try, but we were just trying to get here first. So.
And I forgot to mention it. DOA, putting your antenna pattern in there, also genius. Keep going. The information available in your standard. You don't get to go back and rewrite a lot of that stuff.
Right.
So more info, the better if you can fit it. Good job.
Thank you. Any other questions? Harvey.
Just kind of thinking this through. What are the things that we should be working at as a group? I think it's important that we set early. We work together to set the requirements, what we want the standards to develop at. It shouldn't be, yeah. It shouldn't be one person's or one group's standards. It needs to be thought out quite. And the other thing is, on the lion's share of this is being implemented by UHF television, and there's still about there's a pretty big universe of VHF stations, and I'm wondering, because we have these, but other stations have VHFs. What would be the pluses and minuses for embracing VHF coverage for 3.0 implementation for PNT?
Actually, I mean, this all the algorithms you saw runs on the digital domain. So for the VHF, it's just the power is low, but it travels further. So once you demodulate it and comes in a baseband signal, I mean, there's no difference in our algorithms.
Antennas. What do we do for antennas, right?
And geography, right? If you want this thing to go worldwide, I'm not a broadcaster. I don't know that space well at all. But the situation that I come from in aviation is things always have more energy and support the wider geographically you can consider. So to the question, the idea that you've got a digital solution here that can be imprinted on different RF bands, that also is of high value. What that value is, I don't know. Again, I'm not a broadcaster. I don't know the difference between Canada and US even, let alone Korea, India, wherever else. But I think the more you have in that RF domain at your disposal, the more power,
Yeah.
as in economically, you can leverage.
You touched an interesting point. One thing we do not talk about, but we have plans to look into the future, is the propagation of this television signal out in the space, especially in aviation space. Because television signals, you can think about, is 1,000,000 watts. I mean, the lobes are, it's a little bit tilted so that it goes to the users. But even if the side lobe is 30 dB down, a million watts 30 dB down is still a lot of power. And just an estimation shows that it should travel a few hundred miles. So now, if you're flying a drone, I mean, the reason we do not discuss it, because we actually haven't done the measurement, because it's a different propagation model. It's a free space we could estimate. But also, for the planes, there will be a lot of Doppler. We haven't tested ATSC3 for that high of a Doppler. It was not designed for that. It was designed for like a 180 miles per hour, so it can handle. But once we transmit the signal, there is always opportunity for clever people to find with clever receiver algorithms. They'll figure it out. And so that is an opportunity in the future. Once we solve things on the ground, we could also start solving things at a few miles up for drone and planes, and it would be totally, that signal will give you much higher accuracy because it will not have multipath.
I'm not trying to hog the mic, so other people come with questions, but these are exciting. So immediately goes to time to first fix, a classic problem. And the situation that you're able to get bootstrap at minus 65, is that what I'm seeing?
Yeah, that is, minus 65 dB. That is low power for broadcast, but if you think about a 1 million watt transmitter, if you have a 10 miles
Oh yeah,
away from
don't make me do math. Oh my God, it's the end of the week.
Yeah.
What I'm saying is time to first fix on a bootstrap, there are companies that made their entire claim on time to first fix and really did make it. If you can aim in digital TV for a moving handset, time to first fix, that is something to go after. I had the conversation with Mark last night. Start figuring out what the scope is on the specifics in minimum operational performance standards for the handset. This thing takes off.
Yes, the time that was a very good observation. Time to first fix theoretically is what's the frame is. Like you receive frames from multiple towers, and once you have the frames, if you have a fast enough computing platform, you could just compute fix.
Yeah, but so you're closing on a DLL or an actual phase loop?
No, it's you can have a BPS receiver will listen to, say, 5 television stations it's listening to. Yeah. It's getting the bootstrap and the timestamp from all 5. So it has to wait until it gets all 5. That is the actual wait time. And you get the signal once every frame. ATSC3 frame is configurable. Right now, broadcasters use about 200 millisecond to half a second frame. But the standard allows it to be 50 millisecond. You have 5 seconds, and on the other side, 50 milliseconds. So if it's a 50 millisecond everybody uses, theoretically, time to first fix would be 100 millisecond, because it's depending on where others are coming.
Got it. And now I'm going to hit the tennis ball back in the other court. Russ, these are the kinds of things that you need to bring the multidisciplinary to. These guys are doing great work. Don't go solve all those problems in your own box. There are other domains that have worked these problems, and you know that there's richness there. This is exciting stuff.
Okay. Yeah. Yeah. Because yes. Yeah. 2 frames.
That's a very big lever.
Yeah, that's an interesting idea. We actually mentioned some of this on our first paper. The way some of the other things that we could do is in difficult situations when you have a television. I mean, you can listen to the bootstrap or preamble, but you cannot decode the channel. You do not know the location of the tower, like from 4 stations. But you can listen one, you can decode one. But if that one tower transmit all the neighbor position and the neighbor location too in the message structure that Mark was showing, then you do not have to receive a packet from all the stations. If you receive from one, and you could get the information from others. So that will make the system threshold to whatever is the lowest, like -9 dB from -5 dB. It's just, I mean, there are even if you go with the bootstrap, there are also tricks for it. Then the system threshold will go to -12 dB SNR. So these are things we will transmit. We plan to transmit everything, and we have designed the messages so that we know which elements people usually use for clever receiver design or location design, and then we rely on the receiver depending. I mean, these are expensive to design, but if there is a market for expensive receiver, very resilient, robust receiver, it can be designed just based on the information.
Oh my word! I mean, the first GPS receiver was $200 million. 50 cents now. The more information you have available, the more people can innovate.
Exactly.
It'll work.
Sorry if I get too much into the weeds here, but that timestamp, is that TAI time?
Yes.
And does it also include leap second time?
Leaf second is a metadata that passed on the BPS
Okay.
infrastructure message.
Okay.
Yeah, one of the reasons because that's in the standard, and television is we're in the business of showing you nice pictures, and audio and video, and we do not want like jumping in the time. We want monotonically increasing time. That's why we use TI. But the metadata is all available. It's just 2 bits, 3 seconds or 39 seconds.
Help
That
but
is.
notice you referred to that timestamp as time of arrival estimated, not time of transmission. I didn't understand.
Timestamp is timestamp. The one that we we embed in the preamble at the time of the transmission from the reference point of the antenna. If there's a meter or whatever reference, but that's what we transmit.
Yeah, just the name seemed to be. Okay.
On the receiver side, you have to think of this time of arrival and then measure.
Thank you.
No. I just want to touch on the positioning side of things. So as I see right now, the whole thing is based on multilateration, and so using pseudo ranges to calculate the position. But in the future, you have talked about that there would be some masters, and then you would have different base stations which are masters, and then you will have other stations which might not have a cesium clock or something. So that makes it more like a time difference of arrival kind of system. So are you guys thinking about hyperbolic positioning and also, or you will only pursue the pseudo range or multilateration? First question.
Yeah.
And the second is what kind of accuracy you are finally as a vision for the system. What kind of accuracy you are expecting? Especially like in urban environment where the GNSS suffers, and we are trying with the low cost inertial and everything, but if you see autonomous car, they are mostly dependent on LiDAR or cameras and everything. But if such kind of systems can give us a better accuracy, why can we use this or not? Like what kind of accuracy you are expecting?
Okay, yeah, those are really timing PNT type of question. I'll answer for everyone. The first one is multilateration. We we're thinking about pseudo ranges because if you have 3 towers, if you use hyperbolic method, you get 2 independent equations. You get 1 less. But we using pseudo range, I mean, you cancel out the time. Using pseudo range, you have 3. So since this is almost like GPS, I mean, this is we simulated it in the first paper, and this is oh, okay. Oh, all right. So I mean, it's the way most GPS receivers are done. It's a textbook case. We use pseudo ranges, and we estimate joint estimation of X, Y, Z, and T. So that's the first question. Second question is the accuracy. That one we do not know yet because we haven't tested, and it will you know look, you are very, I mean, from a question I can sense that you know all the issues because it will depend on the unresolved multipath. You can have multipath, but as long as the first one you could detect the first one, so that is a time of arrival. But if that has the first one is not line of sight, it could be low. It has a residual unresolved error that will show into the fix. So it will depend on that. And so that means like how long is the TV station, how high, how much multipath in the terrain. So that is one factor. And the second factor for the accuracy would be it would be GDOT, geometric dilution precision. It's basically if you have many towers and if all the antennas are on one tower, then there's no diversity as the signal is coming. So you try to draw 2 circles. The centers are really close, and you try to find where they intersect. Then you see the circles kind of smear. You do not know where they intersect. You want the centers far away so that it has a nice cut. So television stations, that's a very good question. Usually it was designed to deliver pictures. So if you have antenna, you don't want users to go every time change antenna. So it helps for us to put it where it has a high ground, somewhere central location, and put most of the antennas at one place. So that is bad for the GDOT. So that is one thing we'll be fighting against. Although we can have 17 towers, you might find out that the real locations are maybe 7.
Yeah, sorry, you're gonna have that one person with the dumb question, but so considering, you know, the robustness that you're building into the system, I'm assuming that you're developing it so that it can go beyond just giving redundancy to the GPS system, right?
We are designing it to be complementary to the GPS. You can have GPS, hopefully GPS and BPS will become in one receiver.
Okay, so then the way that you want to implement it is to integrate it as a complementary aspect. No. Yeah, I know. It's complementary is when they can they work together to achieve their goal, not necessarily that one needs the other.
This one, I mean, the broadcast system can operate independently.
Yeah.
Right? Without GPS. That's sort of the point.
Yeah, that's what I mean.
To,
yeah,
right?
that's
Doesn't
what I
have
mean. Is
to,
like it sounds like the
can.
robustness that you're putting into developing the system allows for stuff that is just beyond dealing with GPS. That's
No, it's not, and a lot of the time, like the graceful degradation is the thing, and a lot of engineers design that way. Like you have 3 GPS satellites. What do? You have no location at all. You need at least 4. 5 is good. 4 maybe on the surface of the Earth you could position, because one of the ring would be the sphere of the Earth, surface of the Earth. But if you have 3, you cannot locate. But like 0 location, you get it from a good location to 0 location, and this graceful degradation and hybrid algorithms means that okay, you have 3, but you can listen to a couple of BPS towers. Why not take the range rings from the towers and merge it with the GPS pseudo ranges? Then you have There is something work to do because the GPS, the pseudo ranges are really big and hybrid. From BPS it would be small, 50 kilometers, others 1200 kilometers. If you're familiar with this fixer algorithms, when you do a gradient, it's you have to do gear shifting and all those things. But those things are understood and people can do those things. You know, they know how to hybridize the range. So it will be a gradual degradation. Then if you have 2 GPS, you could use 3 or 4 BPS towers. Your positioning accuracy might degrade, but you'll get something. Your time will something.
Yeah.
So that is what we're thinking about.
So to both complementary as independent systems that can work in complementary, but also like can support each other with the graceful degradation.
Yeah.
Yeah. Okay.
Oh, Andrew?
You're onto something exactly. And what's going on there is that systems or service providers might be putting out lots of signals, but you as the user get to decide how. That's the complementary nature. Your handset could say, yeah, right now, life's good in GPS, or for some reason I know it isn't, start using these other things that are always around there, the BPS on one side. So the complementary nature, and this goes all the way back to policy, not just what should a commercial entity or the government provide as signals, but how should a handset or your user device take advantage of those, and it should do it responsibly. You're definitely onto it.
Just keep in mind, a complementary system that is capable of operating completely independently, that is a genuine complement. And being able to take advantage of the goods of both or multiple complementary systems makes this whole thing more resilient and makes it better. That's why this is so interesting, because BPS is a completely independent environment. And we should use that to our advantage and not consider it to be a disadvantage.
Hello. I think I saw on one of your slides earlier that your accuracy of your timing network is accurate to 100 nanoseconds. I just want to know what's your goals to improve that? Or is 100 nanoseconds good enough? I think somebody else asked a similar question, but I just want to know what's your end goal objective.
Yes. Sam Anthony showed a slide of the requirements of the autocritical infrastructure, and 200 nanosecond was the limit. Like, looks like if we can meet 200 nanosecond most of the time, I mean, you could for usually this accuracy comes. Nothing is ever guaranteed. You could have 95% of the time or 99% of the time you get certain accuracy. If it's 200 nanosecond, that meets all the requirement. But we are trying to tighten the budget at the transmission side because we do not have a control on the reception side because it will have multipath. So if it's a user, like who doesn't care that much, you can have an antenna over here, you can have some multipath, like you're off by, you will not be jittering 200 nanosecond. You'll be offset like about 200 nanosecond or 100 nanosecond or 50 nanosecond. It will be jittering a few nanosecond around that. So if that offset is very important for you, if you do not want to, if you want to take it out, then one option is mount an antenna high enough so that you have line of sight. If you're a serious user, you should do that. You could have other means too. You could, if you know another system that measures the time very accurately. So if GPS is working over there at that location, you have a free sky, multipath is coming from 5 miles away towers. You could calibrate your system that when the television BPS comes, it has multipath, it cannot resolve 50 nanosecond or 100 nanosecond. But GPS, you see the real time. So that's a calibration offset, and you calibrate it out. So you take the BPS time minus that offset, then you get a time. So those are like, there are ways to solve those things. It becomes expensive. You have two things, like calibration, but in terms of technology, I mean, these are well understood methods. I'm not the first guy saying this. These are used everywhere. People use GPS for what?
We had 200 nanoseconds for all critical infrastructure. We were trying to get to 100 or better. That's what we were trying to do. I think what we demonstrated here today was 25.
Yeah.
Okay, yeah, so just to like really simplify it, Tariq, you told him, he asked what time it was and you told him how a watch works. 200 nanoseconds was critical infrastructure. Our goal was 100. Today we demonstrated 25. Right. Yeah, no, and please, a round of applause for these guys, all three of them.
Yeah. But
because Tariq's telling you we can do better.
The second part of that question, what is that then? So what's your maximum that you guys think that you can achieve? And this is
Well, so I'm gonna answer the question differently. We were told by some expert in this room that we could stop now because we were good enough, and we should focus on other areas of the system. And so that's not to try and I think we can get to 1 nanosecond. I mean, maybe, I don't know.
Doesn't
But
matter.
the advice we were given was that there's enough other areas of focus in this whole system that our accuracy is good enough now, and that we've got to work on other aspects of the system.
we're plus minus 10 nanosecond of the reference now. I mean, we don't get any more benefit out of it.
The reason that I bring that question up is it relates to, I think, the accuracy of the end position, right? And how accurate can you get to GPS grade today is plus or minus 3 meters on the ground, right? And what is the position that you guys are going to get at the end of the day? Is it going to be plus or minus 10 meters, 25 meters, if it's 25 nanoseconds? And that's where I think my question is coming from.
I don't want to take them off the hook. Tariq, you still got to answer the question. To go specifically to GPS, there's a lot of GPS experts in the room. I spent a lot of time there. 3 meters was never dreamt of in the day. A kilometer was a success. By doing the right things with standards and going to academic communities to let other people think about things, it gets out of the mindset of how do I take this solution that I think I built and owned and drive it to some number, 1 meter, 1 nanosecond, whatever it is. I think that's the advice that Sam is talking about that we've heard. They put a stake in the ground. There's a lot of people that are going to carry that further, but the big problem now isn't saying, are we in the realm of a valuable service? It is how to get that service from the transmitter to the receiver. It sounds like you might want to go back to school. This is great, right? A classic one on error is bias versus noise. I think that's what Tariq was also trying to get to. There are techniques for both of those, and they depend on the application. And you can drive a long way, and the smart brains in this room are going to be the ones that get you there, rather than simply one group of people saying, hey, here's where we could go. To flip that coin, if I had to make a guess here, not putting pressure on them, I'm pretty sure they can get down the ones and nanoseconds without too much trouble.
I kind of had a feeling that I was just looking for the team here for sure. I think there's a lot of research that shows that the timing actually can definitely be brought to very synchronous rates in the picoseconds. So I think it's definitely possible. Just wanting to know your opinion.
I have to admit, I'm the one that he just accused of telling them this is good enough. And the reason I said that is there's so many other things to do in order to change policy and make this system acceptable and used. You have to set a threshold on how much time am I going to spend dinking around with it and how much time am I going to spend making it a real thing. And believe me, 25 nanoseconds of high precision, very deterministic across the country is more than good enough. And now we can start on the policy process. Not to say we won't try to make it better, but let's solve the second problem before we solve the first problem twice. That was the reason for my advice.
Yeah, another thing I want to point out is that when did we start on this? Was it last March, last April?
About a year ago.
Oh no, we started phase 2 in December, around
Yeah.
right after NAB. Yeah, but the one before that, we had 6 months to get to phase 1, and this one we started in May, and here it is November, and we've got this. So tech is not the problem. The tech is not the problem. But I've known that for a long time. We've all known that for a long time. So. Yeah.
That's what policy is. That's why it's not technology. The community of people that utilize the service, the community of people that utilize the service in a critical infrastructure environment, there's millions of them. And there are millions more of them like us that depend on them doing what they're supposed to be doing and getting what we need to us. That's the bottom line here. This is a risk mitigation issue. And believe you me, we are at risk. So we need to understand when the technical capability of a system satisfies risk mitigation, and then we begin the very long, hard process of changing the rules and the mindsets and the approaches that we utilize to measure that risk. And that's where we are today. And I thank you all for being here because you're going to help us do that. You are going to participate in this. So great.
Behind you.
So just, I don't want to get myself in more trouble. But a couple of comments, I think, and then a question for Tariq and the group. Thanks for the great presentation. So when people talk about 10 meters and you mentioned 3 meters, the industry standard and what we expect for GNSS today, last year, and the years to come is about 2 centimeters. So it's about an inch, 1 sigma horizontal. That's high quality. So when we talk about precise positioning in GNSS or just in positioning and navigation, we're talking about a couple centimeters. So we haven't talked about meter, or we don't use meter. We haven't used that for a long time. I know that for the majority of the world, that's what they're looking at, but we don't look at it that way. And big part of the reason is the corner cases. If you're getting 3 meters or you're aiming for 3 meters, then what's out at the tails? What's out at the tails might be 100 meters. So if you're talking about a car lane level navigation, unless you're in Australia, out in the outback, that's not how wide a lane is. So the targets that we have for GNSS and PNT, I do want to point that out to everybody. They're orders of magnitude different than I think what people are thinking of when they take their Garmin out, for hiking. And this is coming now directly from the constellations or from service providers. And we've been doing this for a while. This isn't new. The real interest, right, is when we talk about resilience in GNSS PNT is interference, is spoofing. Spoofing maybe a little less so, especially in friendly environments. Signal blockage, like I said, just having the open sky. Those are much bigger issues. So what Pat's saying, I completely agree, right? But in terms of just the everyday industry, the research, the engineering, the science, this is how we look at it. So I think our in many applications, the goalposts are in a different place. But that's not to say that especially critical infrastructure, timing, all of this makes great sense. So that's my comment. The question then is, what do you see right now as the error budget for PNT for the broadcast solution? I know that it's difficult to quantify because, how many towers you have, how high are they, the transmitting capability, the geography. This makes it very, very hard to quantify an error budget. If a customer says, I want to meet this minimum standard all the time.
Yeah.
And then can you speak of what the biggest issues are? So for example, multipath, is there theoretically a maximum amount of multipath that can occur? And what are some of the other error sources? So I think of, let's say if you have a cesium clock at a master station, and I'm thinking the GPS, version, but then these clocks are continually synchronized.
Yes.
They're paper clocks because the clocks themselves drift. And so that's having an atomic clock at a reference station ain't good enough, right? There needs to be much more. So can you speak a little to the error budget and maybe orders of magnitude? I don't know if it's possible. Thanks.
Our first of all, our goal has been to provide time. We're not thinking about providing location. Remember when Sam had a slide, he highlighted critical infrastructure, 3 of those: power grid, cellular wireless, and financial transaction. All 3 microsecond is the requirement. So this is a complementary system. It has a limitation, but I think we could deliver microsecond type of accuracy, like 99% of the time, or even more. I do not know. When you deploy, we'll know. That is the problem we're trying to solve. We're not trying to help the Uber drivers yet. But as Andrew was saying, someone is clever enough and do a lot of research and so figure it out. Yeah, good. But we don't. Our budget is, our target is time. Budget is 200 nanosecond or less than 1 microsecond.
To answer your question, what is the error budget? Very simple. How good is your clock? Because that's your error budget. To perform, actually, let me give you an example.
It doesn't matter how good your clock is, it'll still drift, right?
Let me give you an example. NASA wants to send people to Mars. Okay, that's fine. I'm not going. But they want to send people to Mars.
But they don't want to bring them back.
Well, that's why they're very selective on who they send. The real question is, today when we launch a spacecraft to some place, that spacecraft is in a continuous state of communications with the Earth to find out what time is it and how far have I traveled, because it doesn't know. And NASA came to the realization, wow, if we miss Mars by 1,000 miles, we still miss it. There is no turn signal, right? So what NASA has done is they've created this thing called a mercury ion clock. You probably never heard of that. That they're going to put in the space machine, in the space capsule. The mercury ion clock has been going around the Earth now for 1.5 years, and it has not lost a nanosecond. That's the error budget. How good is your clock? Because that's what drives this entire thing, is how good is the fundamental clock that's at the core of it. So everything that happens after that adds to the error budget. But if you really want to get good, like NASA going to Mars, you better build a clock that's capable of doing that. And that's a limitation that this organization and that policy is not going to have an effect on. What we have to do is identify ways to de-risk our use of this capability in the execution of our normal lives. And the error budget we have today, in my personal opinion, is good enough.
But to Andrew's point as well, this thing's 50 years, GPS is 50 years old, and people like yourself have been working on it for 50 years. We've been working on this, half a dozen of us for 1.5 years. So I'm just saying, if we put a lot of smart people on it.
Yeah, and you have 12 PhD students.
Yeah, and people start writing
if you
theses.
think about the brain power you have, it's not just 50 years, it's also.
Right, so, plus we have compute now that's much, much better too. So, yeah, so
and to
it'll
answer
move
your
fast
second,
once we get it. The problem though is we got to get it deployed. I mean, until policy changes, this is just not a thing, an invention, right? we've got to get it out there and going.
And
And
to answer your second question about clocks, we have spoken with some clock manufacturers, and they told us, I mean, they know they have been working on this. They told us, they can have this clock. It's like how accurate we want. It's a function of money. You can have like one configuration. You can have 2 cesium clocks. You can have one GPS coming in with the beamforming antennas and anti-spoofing thing. You could have STL in there, different iridium constellation time, and then you can have dark fiber backup, and they can also have a fiber, that is because of the symmetry that is measured using GPS. It's very accurate. They say that the fiber could get like 10 nanosecond. The overall thing they call the EPRTC is the budget is less than 10 nanosecond. I have never tested it, but yeah, it costs more than a Rolls Royce. So it depends on how much money is spent, but the solution is there. We don't have to invent it. It's just spend money and then you get your product. It's there.
So I have a question. So it's so exciting. How about the receiver manufacturers? Are they on board? Are they saying we can make you a $5 receiver, or it's $5,000 right now? Are you getting any interest? Are you looking for industry partners there, or is this the man?
He's building up.
He wants a patent.
Yeah.
We want the market to be free to use. So as broadcasters broadcast the signal, just like GPS satellites, you do not have to pay any royalty subscription fee. So it's free to use. And if there is demand, and demand actually comes from policies, if the government enforces policies that, if you're on a power station, you cannot rely just on GPS. You have to have a second one. And then they will buy these things, and that will drive the market. It's not that the broadcasters are making money out of selling devices, although some could, but you also can make a device and compete, make a very clever device that does better than this.
So my take is yes, we do want industry partners. That's why we're here. I mean, I'm just like, again, I'm going to raise up a little bit. We're here because we want to engage the academic and the commercial communities to be aware of this and to make their own choices as to whether they would like to join us in investing in this. So at that level, the answer is yes, and we would like, partners in it.
Were there any more questions? Oh, Tony, here, we'll get you a mic.
They want to do it too.
As a receiver manufacturer, thank you for that. I appreciate that. Another thing that's interesting that we haven't really touched on just a little bit, Tariq, in the beginning, is that once these physics, table stakes of the bootloader and the preamble is resolved with soft combining and really smart software and devices that do really interesting things to combine signals, and we get it to a really great performance. There's also the payload piece that we haven't really talked about as a complementary system to other location systems. That information can be put into that payload to help augment the accuracy of the existing system. So as we get into these situations where we're in an MFN or an SFN or out in an area where there's fewer towers that we can actually see, we can benefit from the payload data containing more stuff coded at different mod code, right, depending on the topology, to help benefit the complementary systems that we're trying to help. So,
Actually, there's one broadcaster who said they operates 200 stations. They have plans to do that. They're already doing it. Yes, they have RTK solution.
One more question. So just building on that point, that obviously this has a much bigger broadcast range. have you thought about the use for this of transmitting as well, particularly in remote areas where you don't have cell service? Like I know Apple these days has added their SOS for emergency phones, something like that.
Yes, that's being worked on. Something like that is being worked on. That's a different hat I wear that I'm not talking about today, so.
Were there any other questions?
It's experimental, so. Yeah, more. Right?
Kilometer and a half,
Yeah.
just northwest here.
1.4 kilometers.
Next campus up.
It's just north of Finch Avenue here at the Humber Trades Technology
I
Center.
don't know what it is. It's pretty flat here.
I heard it's not even line of sight.
Yeah.
No. You can see.
ATSC3 reception is world class. It is the best of the world. I say that out loud, and it is true. We've done the comparisons.
Clever receiver.
On that note, I think we're done.
Yeah, unless there's any other questions, I wanted us just to all collectively thank Mark, Tariq, and Vlad for a very robust conversation and a very educational, informative presentation. Thank you.